Okay, for today, we were looking at a little bit of review for the retake tomorrow. And students were presented with this setup where we had a charge of 2Q and another charge of positive Q. And it says which letter is closest to the position where the electric field is 0. And I gave students a few minutes to think about this. And specifically, my hint was to think about the electric field vectors from charge 1 and from 2 over in this region, the electric field vectors here and electric field vectors here. You should be able to come up with 2 of them in each of the regions and figure out where it might be equal to 0 at. And students said that it was somewhere in between here, and since this charge here is positive 2 and this one's just 1, it must be closer to the smaller one. So students reasoned that it was D, and they were correct. The next one they looked at was positive 2Q and negative Q, and where that electric field is 0. And again, students were thinking about the electric field vectors over here on this side, over here in the middle, and here on the far right. And they're trying to figure out where would the electric field be equal to 0. And students unanimously said over here at E, and that's because electric field vector from charge 1, which is positive, would point to the right. An electric field vector from charge 2, which is negative, would point to the left. And so over on this side, it could possibly equal 0. The reason it can't be over here, because you might be thinking, there's right and left here, is this is a bigger charge, and so it could never be equal to 0 over here. So E is the right answer. And then finally, they were presented with equal magnitude, equal polarity charges, and had to figure out where the electric field was 0. And students said, trick question, Mr. Limpesti. There's no location. And they're right, there is no location. Then we started on the electric potential worksheet 1. We actually did a little bit of this before, but we did a little bit more just to review. Figure out the regions of low and high potential. The high potential places are where the potential surfaces are closest together. And the places where it's a low potential is where it's really spread out far apart. Number 2 is looking at the exact same configuration, and we're trying to figure out the electric field vectors. Well, they're always perpendicular to the equal potential surfaces, and they always point from high potential to low potential. We also have to take care of the magnitude, how long the arrows are. And they're longer where they're tighter packed for the equal potential surfaces. So that's what it would kind of look like. Then we went on to number 3. Number 3, we're looking at how much work is done by an external force to move it from A to B. And this is kind of difficult because really if you want to figure out the work, that's equal to the summation of the force dot dx. This dot product, if you think about it simplified, the way we looked at it last year was force times the distance, displacement times the cosine of the angle between the force and displacement. Well, that force changes direction. Over here, the force is kind of this direction, and then it starts kind of rotating around. When you get on this side here, it's this direction, and it just keeps on changing direction. Over here, it would be right along the line. Over here, it'd be perpendicular, and then it's perpendicular to the surface here. And so it's very difficult because that angle changes. So is there some other way we can do it? And we talked about this last week. Yes, there is a different way because work is going to be equal to the change in energy. What kind of energy is changing? Well, that is electric potential energy. So Q times delta V, which is the voltage. And so that would be 15 times 10 to the negative 6 coulombs times the final voltage minus the initial voltage, and you get negative 7.5 times 10 to the negative 4th joules. However, we need to figure out what is the work done by? If you're thinking about taking an external force and moving this charge, which is positive, from here to a lower potential at B, Well, positive charges naturally move from high potential to low potential. So this thing would actually accelerate. We don't want it to accelerate. We're going to take an external force and move it there at constant velocity. Well, that means our force must be pointing from B to A in the exact opposite direction of our displacement. So the external force is going to be doing negative work. However, the field itself does positive work. So the field does positive 7.5 times 10 to the negative fourth joules. But the external force does a negative amount of work, negative 7.5 times 10 to the negative fourth joules. And then there was another question that says, how would the answers change if the polarity of the charge was negative? In that case, it would just be the opposite. The field would do negative work, and the external force would be doing positive work. Okay, then number 4, we're looking at calculating the electric field strength between B and C. So in this region, we're trying to figure out how long that arrow is. Well, we know that work is equal to force times delta x. It's actually the dot product. It's force times displacement times cosine of the angle between them. But in this region here, it looks like that angle is 0 degrees between the force and that displacement. Well, the work in this case is equal to a change in potential energy. So Q delta V. Delta V is voltage. How do you find the force for moving this charge? Well, that would be Q times the E field. The Q's cancel out, and we figure out that the E field is equal to the change in voltage over the displacement. Now, this is only true when you have a constant electric field. And you notice how these electric potential lines are parallel to one another. That would tell us that we have a constant electric field. We can plug in, we have 10 volts divided by 0.02, and we get 500 volts per meter. Remember that electric field can also be measured in newtons per coulomb, so that's also 500 newtons per coulomb. So this is the first case where we've found a relationship between the E field and the potential, the voltage. And this is going to be important to figure out the charge on an electron, the quantum amount of charge on anything, the smallest amount of charge. Okay, then number 5 says, what is the potential difference needed to stop a 5 microcoulomb charge? And I forgot to put in what the mass of the thing is. So let's say with a mass of 2 times 10 to the negative 12th kilograms, it initially has a velocity of 5 times 10 to the 5th meters per second. Well, at first this thing had a kinetic energy, right? Well, where did that energy go? It had to go somewhere. It turned into a potential energy. So Q delta V, and that's going to be equal to 1/2 mv squared, where V in this case is velocity on the right-hand side. So that means the potential, delta V, is going to be equal to 1/2 that mass times the speed squared divided by the charge. And we get 50,000 volts. Okay, then the last thing we looked at, we whiteboarded all those problems, by the way, 1 through 5. Then we did a little bit more review for tomorrow's retake. We were trying to figure out the electric field at A for this sphere over here that has a charge of Q, and at B for this sphere over here it has a charge of 2Q. And students said, Mr. Lentfest, you're trying to trick us. Because what are these? What kind of spheres are these? Very important question. You're right, I am trying to trick you. If this was a conductor, then the electric field at A would be, and students said it was 0. So we said that these two things are actually going to be insulators, and the charge is going to be distributed uniformly throughout. So that means the density over here is a constant charge density, and this one also has a certain constant charge density. So we're trying to figure out the electric field. Well, of course we want to use Gauss's law. Closed integral E dot dA equals Q enclosed over epsilon naught. The E field would be constant, and the area on the left-hand side would be the area of a sphere, 4 pi 1/2 r squared, because we're talking about through A. On the right hand side, the part that's hard about this is figuring out the Q enclosed. It's going to be a proportion of this total charge Q, and it's dependent upon the volume, the ratio of the volumes of the smaller to the larger. So 4/3 1/2 r cubed over 4/3 pi r cubed. That simplifies. The 4/3 pi cancels, the r cubes cancel, and you just have 1/2 cubed. And that simplifies to q over 8 epsilon naught. Likewise, on the left-hand side, the 4 cancels with the 1/4, and we have pi r squared. And then finally, we get q over 8 pi epsilon naught r squared. On the right-hand side, again, we want to use Gauss's law, closed integral of E dot dA equals q enclosed over epsilon naught. And on the left-hand side, it's just going to be E times 4 pi r squared. On the right-hand side, it's going to be 2q over epsilon naught. And we get q over 2 pi epsilon naught r squared. So we can see that the electric field through B is actually 4 times greater than the electric field through A. And you might want to think, well, how could we get these things equal? I'll leave that up to you to think of.